Now, after the stiffness matrix has been already derived, and we started with a known or sort of an unknown displacement vector that we described on the basis of the element type we chose, the last thing left to complete the description of the equilibrium equation is the load or the force vector. Now, since we have been talking consistently with the minimum potential energy or the minimum total potential energy approach, then the force vector is actually coming from the work done or the external work done on the system. So we can look at the work done on the system as U transpose, which is the displacement times P. So in a vectorial notation, where of course you have WE as the external work done, U transpose as the displacement vector, of course displacement vector transposed, and P as the load vector. Now, to find out the force vector or the load vector, you have to do a partial derivative of WE with respect to U, which would basically end up as P, and that would give you the load or the force vector for your problem. Now, in the case of a triangle membrane element, yeah, it's very easy because it works very intuitively. If I have certain concentrated loads at certain nodes, then I know how to apply them because they are just basically point loads which are acting on the system. Now, so if I have just a force vector P, which is written as PIX, PIY, PJX, PJY, and so on for, let's say, PKX and PKY. So I have 6 different loads acting, and whichever ones are acting, I leave them, or I substitute the value -100 or whatever, and the other ones remain as 0 as an example. Okay, so these are just concentrated loads. So there's nothing fancy about it. However, when the load type changes, so for example, if I have a triangular element and I have a distributed load which is acting on only so if it's a a constant or uniformly distributed load on one particular edge, which is given as ij, then I have a load which is acting only on the edge ij. So if I'm going to write the load vector P, then I automatically know that the loads related to ik and jk are nothing, right? So it will only be at I and j. So k doesn't have anything on it, so I get 0 here. However, there will be a distribution of the load, so I will have to use something else to fill up these particular parts. So this is not 0, of course, there will be some values here. So I need to fill it up. And how do I do that? For that, I need to start with the description of P to be equal to the shape function, or let me just write it as N transpose times P, or any kind of load that is acting. I can also call it F. Yeah. So this would then become my final force vector. So as a rule, again, as we have done before, if you want to find out the load on an element in which you have the in which you're doing some kind of transformations or etc., also with the coordinate system, and if you have loads, then you must always multiply them with the shape functions. And of course, these loads are the shape functions are much better suited when you have distributed load acting across edges. So once you apply this particular shape function, you will see that if you have a distributed load, then it will divide the load at this node and at this node, and you'll be able to find the values in the certain direction. So you have to find, of course, the components in x and y, and then put in px, px in both directions, and py, py. So that's about the force vector. So don't forget to use the shape functions when you are deriving the force vector for these systems. And of course, it goes without saying, if I have a local to a global transformation for a certain direction, so basically in terms of the direction cosines, then the element P is going to be equal to the transformation times the local P that you have just derived using the shape functions over here.